We're going to talk about the electric potential of a continuous charge distribution today. So whenever you see that continuous distribution, you know we're going to be dealing with some calculus here. So we'll review for point charges. From that, we're going to develop an equation that that involves an integral. And then we're going to do three examples: a uniform ring, a finite line, and a uniformly charged sphere. We'll try and get through all of that. And then for some of these, you can use, if you have the voltage equation, you can take the gradient of that to get the electric field. So we'll do that for a couple of them if we have time. All right, so let's begin. For a point charge, if I've got a little point of charge out here in the world somewhere, then and I want to know, okay, this location in space way out here, what is the potential that exists there? We know that that potential, V, is equal to KQ over R. And, no, it's zoomed out too much. So, and the nice thing about this is that it is a scalar. You know, it just has a magnitude, no direction. And what is it? It's a measure of how much work per unit charge on my test charge, which would be right here, not the charge over here. This is Q, which is the charge right there. This, you can think of this as being Q naught. And I have to push Q naught from infinitely far away where the potential is zero and do work against the electric field to bring it to this location in space. And this is how much work I have to do per unit charge. Now, if this is just Q1, and I want to find if I've got more than one point charge, here's Q2, and maybe up here is Q3, I have to do work against the electric fields for all three of these, and I can just add them up. The principle of superposition applies, and so the voltage for multiple point charges is you have the summation of Q1 or Qi over Ri, and I equals 1 to n is the number of charges you have. Okay, in this case 1 to 3. Now this is a nice equation, again, because unlike the equivalent equation for electric fields, there's no r hat here. You don't have to worry about direction. So it's very, very nice. Okay, well, if I've got charge smeared over some volume of space, though, I can treat little tiny chunks as point charge. So let's say I've got, you know, my amoeba of charge, and I've just got, you know, some charge distribution over, and it's continuously smeared over, you know, this volume of space. And I want to know, okay, at point P right here, you know, what is the voltage? How much work do I have to do per unit charge to bring that test charge from infinity to here, given this charge distribution over here? And so what we do is we pick a little chunk of it, and we're going to call that dq, and dq has its own distance from my test charge r, and I say, well, a little tiny bit of the voltage is going to be k dq over r, and of course this would be dV, a little tiny bit of voltage due to this little tiny bit of charge. But if I add them all up, if I sum them, I get the total voltage. So I sum them all up using integration, And so this becomes, not surprising because we've done this many times now, this becomes the equation I use for figuring out the voltage over a surface or a volume that has charge distributed all over it. And of course, remember that charge can be smeared over a line. That would be lambda. That would be the charge per unit length. Or it could be smeared over an area, and we would use sigma for that. Or it could be smeared over a volume, and we use rho for that. So this is, remember that, and we've done this many times, lambda is charge per unit length, charge per unit area, charge per unit volume. And so the key is to figure out what dq is. And we're going to use these guys to change this so that we need to get dq and r in terms of the same variable. K, remember, is a constant, so it just comes out. Okay, so the best way to do this is to do a few examples. So let's talk about a uniform ring. So let's suppose I've got a ring like this, kind of drawn obliquely there, and here's my central axis. It goes to the center of the ring. Let's give the ring a radius of a, and it's going to, obviously it's a constant. And let's go a distance like this. We'll make this the x-axis. So this is a distance, some variable distance x from the center of this ring. And that's where I'll place my point P. And I'm going to want to know, let's say I've got charge smeared evenly distributed over the ring like this. And it's always nice to start with the ring when we're working these problems, because rings, the r is constant, right? The distance is constant. So let's take a look. Let's pick a little dq. Here's my little dq right here. And I want to know what's the voltage at this point. Well, we need an r. So here's my r. And so I'm going to say, okay, the voltage there is equal to K dq over R. Always write down the basic equation. You guys start with the most basic principle and then massage it into the form that fits the problem. Okay, and I got this dq. But one thing I notice is that here's R, and I can get R in terms of x and a. I think you'll see that R is equal to the square root of x squared plus a squared, right? Here's x and here's a. And also it is a but it's a constant, right? I mean, if you're right here, if you're at a position x, and you notice that r, because it goes around like this value for r is a constant, so it comes out of the integral, and so this just turns into k. Now, when you integrate all the charge, I'm sorry, let me pull the constant stuff out. So k. Now r is a constant, so it's going to come out of the integral, and you get x squared plus a squared, and then you're just integrating all the little dq's. Well, if you sum up all the little dq's, you get the total charge. We'll just call it Q, capital Q, and so the voltage is just equal to K Q over the square root of x squared plus a squared. And there you go. Now, you may recall that this is my answer. I guess I should write given, find, and solve. Sorry about that. Given. We're given Q. Well, this is total charge Q, A, distance x, central axis, and all that. And so what we wanted to find of course, was the voltage at this point x distance away. But let's find something else. Let's find E. Let's find E. And now, we did this problem. We did this example problem. And it was a little bit more complicated than this, because when we were trying to find the electric field, we had to get it in terms of theta, and we had to mess around with it, and it was quite involved. But if I use the that gradient thing, it becomes a lot easier to do. So let's find E. Remember, we said that E in the x is equal to, now I'm going to be proper here. I'm going to use the partial derivative symbol is equal to negative. I'll go ahead and use the del. Why? Because it's going to get you used to it, all right? But everything's going to be in the x-ray. If I give you anything on a test in here, or if you see anything on the AP test, everything's going to be in terms of x. So what we're going to do is take negative partial v partial x. And so what we're going to do is take the derivative of this function with respect to x. Well, let's do that. Well, the kq comes out. Well, let's go dx. I'll go ahead and switch to a full derivative because that's really not going to hurt anything. And of, now I'm going to go ahead and call this kq. But look at this. I'm going to call it x squared plus a squared to the negative 1/2 power, right? Does that make sense to everybody? I just took it out of the denominator. And this way I don't have to fool around with the quotient rule or anything like that. I can just go right to the power rule. And I also have to use a chain rule. So let's continue one more line, I think. Equals negative. Well, if I take the derivative of this, we get kq. And let's take the derivative of the outside part. It's going to be negative 1/2 times x squared plus a squared to the negative 3/2 power. And then I'm going to take the derivative of the inside part, which gives me 2x. Now the negative cancels the negative. Oh, and then when you use this del thing, it's all going to be in the I hat direction. It gives you the vector back. Okay, it gives you a vector from a scalar. Okay, so we'll put the I hat there. And then, so EX, here's my final answer, is the 2 cancels the 2, and I get KQ, I'll go ahead and put the X out here, divided by, let's go ahead and put this back in the x squared plus a squared to the 3/2 power, and in the I hat direction. And there's my answer for E. So here's my answer for voltage, and here's my answer for the electric field. Now, believe it or not, this is easier than finding the electric field directly. And that's why physicists will try to find the voltage equation, and then from the voltage equation take the negative derivative of that voltage equation to find the electric field. And it really does work. And you can check this. This is what we got a couple weeks ago, or I don't know when we actually did it for that. All right. So let's do another example problem. Okay, so let's do the finite line. And, you know, these problems are a little bit contrived because in order to integrate analytically, you have to have a lot of symmetry and you have to have certain special things going on. So let's have a charged stick. So let's say this thing is charged, we got lots of positive charge on it. It doesn't have to be positive charge, but it's good to be positive, All right, and then up here, we're going to have, here's our point P, and we'll call this just a distance A, up the y-axis here. And let's say that the stick has a length of L. And what we want to know is, what's the voltage here? And turns out it's doable. Yeah, we can do this. As opposed to over here, I don't know. Let's just do that one. All right. So we want to find the voltage at point P. So now, first thing you got to do is pick a DQ. So let's make that one our DQ. There's our little DQ right there. And it's going to have a distance like that. Okay, so let's solve now. V is equal to the integral of K dq over R, right? So now we got to fool around with this. And, here's R right here. We can get R in terms of X. So we can say that R is equal to the square root of x squared plus a squared. But unlike the previous problem, this varies. I mean, when my dq is right here, the r is less. When I'm right here, when x is equal to 0, my r is just equal to a. And I'm going to integrate all the way out to L. So this is not a constant like it was in the last problem. So let's work it now. So V is equal to K. Oh, and let's work on dq here. Dq is equal to lambda. And let's say that the total charge on here is Q. Well, now what is lambda? Lambda is the linear charge density. But that's just Q over L, right? You see that that's lambda, the linear charge density? This is a uniform, everything's going to be uniform at first. There's a uniform charge distribution over this line, and it has a length of L and a total charge of Q. So to get the linear charge density, just take the total charge and divide it by the total length. And that's how much charge per unit length you've got. So this is lambda times dx, right? A little tiny length times how much charge I've got per unit length gives me a little tiny charge. Well, that's kind of nice. So let's substitute that in for dq. We've got Q over L times dx over R, but R we said was the x squared plus a squared. So this comes out, let's rewrite it, make it look a little nicer. V is equal to KQ over L times the integral of dx over x squared plus a squared, square rooted. Now, where does x start? It starts at 0. We're starting at 0 right here. And where does it end? Where x ends at L. Now, what do we do now? Well, some of you in calculus, you remember you have all these fancy tricks. I don't know, would you use substitution here, or do it, or you can plug it into your calculator. That's the newfangled way. Or get what is it, Wolfram or something? Will Wolfram do this for you? Okay, whatever. I'm going to do this old school. I'm going to take out my table of integrals. Oops, I don't need to see that. Now, this is in my book. And hey, you're going to get a table of integrals to use when you take the AP test. So I'm looking at this, and I'm saying, what matches what I've got? Somebody went to all this trouble to create this table. I really ought to use it just to make them feel useful. All right, so, well, it's this guy right here. Because I've got constant stuff. I don't really care about the constant stuff, but I got a dx over the square root of x squared plus a squared. Ha-ha! Dx over the square root of x squared plus or minus a squared. So you get the plus or minus, you got a plus or minus over here. So it's already been done for me, so I'm just going to use that. Okay, so this is going to be equal to, and I still on camera. Whoa, let's keep it on camera here. Let's see, kq over L times the natural log of
x plus square root of a squared plus b squared. Plus c.
No, we're not going to use plus c. From 0 to L. Okay. Oh, I lost my place in the book. Great. All right. So let's try to do that. I don't know how to do that. Okay, K, Q over L. We're going to plug in the L. It's the natural log. Now, don't you just like make one of them the numerator and the other one the...
No, you sub in L for x, and then you're going to subtract and sub in 0.
But when you subtract natural logs, they just pile on top of each other.
Yeah.
We'll do that later. You're right. We'll do it one step at a time. So we got whoops. Instead of L, I wrote natural log. We got L plus the square root of x squared plus, oh wait, L squared plus a squared. What am I doing? Sorry. And then minus the natural log of, well, you put 0 in there, you get natural log of a. Right? Because you put a 0, you get 0, square root of a squared is a. Right? Now, I believe...
You can divide it, but it'll change.
It'll what?
It's change the base. Oh, yeah, that thing. How do you remember?
Change of what?
Okay, so when you divide logs, no, you don't do that. Like, no, that is no. Okay, so you're gonna divide your logs. So you're gonna have ln of L plus root L squared plus a squared over ln of a, right? Isn't that, guys? No. Yeah. Oh shoot. Why is a on the top?
Yeah, isn't the L plus root L squared plus a squared? It's like
L
plus a's on the
that crap on the top and then put the a on the bottom.
Yeah.
That's it. Put the crap on the top.
Come on, Mike. Why is a on the top?
It's not Allen times.
Trying to find it.
That's what Ryan said. Not friggin'
A equals 1.
Just can't throw the L and the L next with the L on the bottom.
Well, wait a minute. Wait. Oh, yeah, this is on, I'm sorry. This is on the top.
Yeah, it's on the bottom.
Are you contributing, Sydney? So proud.
Wait, Sydney, you know how to do this?
And there we go.
No, I don't know how to do this.
So like,
Oh my goodness, she's taking stats, but still. Sydney, I love you, but I'm sorry if I don't.
This has all been recorded, so, okay.
this is like, just can't throw the L on.
Forget about a lunch date with me.
All right.
Sydney, I love you.
I love you too. So you can forget about our lunch date.
No, I never get to lipstick.
I'm just kidding.
Yay!
That's funny because I had it reversed. I just remembered it wrong. I went, I thought it was this divided by this, but it's the second one divided by the first one, right? Okay, all right. Okay, so last example, and I got to go through it quickly. Let's do this. Well, No, we're not. I don't want the bell to ring halfway through this, so that's it for now.